I'm picking up where we left off, the product and the quotient rule. Yeah, all right, so we finished this one here with the derivative. Now, I'm going to pick back up with example 1 because once we take the derivative, of course, that's not the end in and of itself. We're going to be using these derivatives, and so we want to modify them after the fact and put them into a more usable form. So let's go ahead then and just expand this out. It looks like it's kind of like a partially factored polynomial. If I distribute the 1, I get 5x minus 3x squared. Actually, I didn't even distribute the 1. I just dropped it. Anyway, y'all didn't know that until I told you. Plus 5x minus 6x squared. Then I write it in descending order, and I've got some like terms there, so that's negative 9x squared. And it looks like I got 5x plus 5x, which is plus 10x. Okay, so there's a nice little version of g prime. I could factor out an x, which would be really cool, because probably 99 out of 100 times when we have the derivative, we're going to be setting it equal to 0, the power of the horizontal tangent line. Because remember, that gives us the possible locations of these local maximums and local minimums, which are optimal values. But not every single one of them is going to be an absolute max or local max or min. They could be like stationary points, like on x cubed. But it's very, very powerful. And, of course, once we set it equal to 0, our goal is to factor. So, anyway, we'll do that later. Now, we did not have to use the product rule on this one, did we? If we knew kind of in the end that our goal was to expand it and simplify it and put it in usable form, is there anything that's preventing us from simplifying it first on the front end? Actually, nothing except your own free will, right? So you should simplify early and often. So if I walked up to this problem, I probably would not use the product rule. I would actually simplify it first by distributing the x and getting 5x squared minus 3x cubed. Now I just got a handsome-looking cubic polynomial. I can use the power rule now. I don't need the product rule. I can use a smaller sledgehammer here. Multiply and subtract, I get 10x minus 9x squared. 9x squared. Is that the same thing I got down here? Yeah, it is. If I commute the terms, it's the exact same thing. So which method was correct? Both. Which method was easier? Maybe the first way. If the second way, yeah, that's what I meant to say, the second way. Also less likely to make careless mistakes. If you have fewer steps in between, that means that there's less likelihood of miscopying something or forgetting to distribute a negative. So the more efficient you are, the less likely you make those careless mistakes. Now, I do it like this on purpose because I wanted to verify to you, which see things one time is maybe it's even a proof to you, not in math though, that the product rule actually what? It works, right? Or at least the power rule and the product rule are in cahoots with each other, right? They actually work. Okay, good. Let's move on to example 2. So this was the noun format, right? When we talked on the quiz about people wanting to take the derivative and putting dy dx, no. This is the noun format. You have a function. It's named equals, in this case, g. You take the derivative of both sides, okay? On part 2, though, we're back to the verb format. Now, I put equals there, but you really don't need the equals. This is an expression, and it's equal to whatever you're going to write. So if you work straight down, you don't need equal signs. Okay, so if I look at this expression, 5x cubed cosine of x, how many factors do you see? Which two? The 5 and the x cubed? Oh, you see 5x cubed and cosine. Very good. That's what I would say. You could call 5 its own factor. But if you remember what I said in the previous section, constant multiples go along for the ride. They're there in the beginning. They're there in the end. So if you have a constant multiple, a scalar quantity that's multiplied, you don't need to elevate it to its own status of your own function. He just gets associated with the closest variable function, which in this case is x cubed. So there you go. Any rewriting needed? No, it looks ready to go. So here we go. 5x cubed is written first, so let's take his derivative first. That's 15x squared times what? Cosine of x. He's just supporting his efforts. Plus, now 5x cubed gets rewritten, times the derivative of cosine is negative sign. Now, notice what I just did there. That's correct, but look at that. How do you like that for notation? Dot negative. Does that bother anybody? It bothers the heck out of me. Mr. Johnson, does that bother you? That makes my skin itch, like under my skin, like the bottom part of my skin, not the epidermis. Because when you're working down very quickly, what can happen if that slides in a little bit closer? Oh, now it turns into what? Minus instead of multiplication. So please do not ever put dot negative. If you give me something with dot negative, I'm going to pull a Papa Bear on you and go, grrr. Right? That's what Papa Bear did when he came home and found someone was eating their porridge. Grrr. So dot parentheses is better. All right. Or, hey, how about this? As you get better and better and you become more and more astute in your differentiation prowess, you could say, hey, the derivative of cosine is what? Negative sine. And is there any rule against bringing the negative out front like that? None. It's the associative property of multiplication. And if you could do that, that saves you a whole line of rewriting. Because with the dot negative parentheses, you'd probably want to go down to the next line and bring that negative out front anyway. So there it is. There's the derivative. We started with two factors. How many terms do we end up with? 2, right? Terms are separated by plus or minus signs. We should probably review that. So you always have as many factors as you have terms. You will always have as many factors as you have terms. Now, let's back up and say, okay, it is National Taco Day, and it is also National Golf Day, but let's say it was also National Make 5 Feel Important Day. Huh? Rachel's Challenge? Let's go ahead and, like, for one day, right, they have King of the Day, they have Boss of the Day, right? Let's let 5 be his own function, just for today. So now we have 3 factors, don't we? So let's go ahead and take the derivative. 5 is in front. It's his special day. Let's let him go first. What is the derivative of 5? 0. Good. Times x cubed gets rewritten, times cosine of x. Plus, now 5 is happy just to be back from 0. That was kind of scary, he said. What's the derivative of x cubed? 3x squared. Good. Times cosine goes along for the ride. And then finally the last one, 5 goes along for the ride, x cubed goes along for the ride, and the derivative of cosine is negative sine. So now if you look at that, we had 3 factors, right? We made 5 feel important. And we have 3 terms. But now it's the next day, and 5 has had his day in the spotlight. What happens to this first term? 0 times anything that's not infinity is what? It's 0. So do we end up with the same thing? Yeah, we do. But we did a good deed, right? So you don't have to let constant multiples be their own function. You can just associate them with the closest variable function. Constant multiples go along for the ride. Okay, sweet. Letter B on your mark and set, you do. Go. Oh, yeah, and then they're left with 2 sin, and then you remind them that that is, in fact, what they're doing. They need to repent for that sin. Mm-hmm. Pre-cal kids. I use them in this class also to talk about foolish mistakes. In jest, though. They're still, as I mentioned in class today, they're still, what, toddlers, mathematically? Yeah. Oh, they think that they're one class away from the apex, right? They're in pre-calculus, but they're still babies. Yeah. Mm-hmm. Oh, awesome. Yeah, he ran for a student senate and got in. So he's now Senator Corby. Senator Corby. Yeah, he's excited. All right, we walk up to this problem. We're like, what's up, problem? How many terms have we? That was a bad one. We have one term here, another term there. That's two terms. So remember, terms we can treat like individual problems, right? Reference your quiz you just took. So we can assess each term separately. In the first term, I have 2x. That could be one of the factors. Cosine could be the other. So if you would like, you can add grouping symbols to help you see associated things. In the second term, do I need to use the product rule? No. 2 is its constant multiple, and that's just one variable factor. So this first term is going to generate, ouch, how many terms? How many terms will that term generate when we differentiate it? 2. So I'm going to end up with 2 times cosine goes along for the ride, plus 2x goes along for the ride, times the derivative of cosine, which is negative sine. So notice I just put parentheses around everything. That's another thing you can do. But before I move on to the next term, look at what I did. If you were my teacher, would you count that correct, at least for the first term? Absolutely. Very good. Good eye. I have the ddx in front. That is a verb. That means take the derivative of what follows. Didn't I already do that? I did. So that's gone. It should not be there. All right? If you are rewriting, it needs to be there. But when you take the derivative, it should go away. And again, I would recommend if you have multiple terms in this verb format, just keep rewriting everything until all of them are ready to go. All right, and now the next term, I use a different flavor here. The negative 2 goes along for the ride. And what's the derivative of sine? Cosine. Okay. So we're essentially done with the calculus. The calculus part is over. It's very ephemeral. It doesn't last very long. We might take 3 or 4 lines rewriting it, 1 line of calculus, and then 3 or 4 more lines simplifying it. All right, it's just one step in the process. So if we were to simplify this, this would be 2 cosine of x. We'd bring the negative up front, negative 2x sine of x, and then minus 2 cosine of x. And we're done? Do we always just walk away? Yeah, I would look before you walk away, maybe just kind of take it all in, marvel at your awesome work. But is there anything else we could do? Very good. We actually have like terms, and they're actually opposites. So they nullify each other, making a 0 pair, and so we're left with negative 2x sine of x, which, as Mr. Johnson said, his students then would factor the x out. Does that work? No. That is math humor, and we all get that joke, right? Silly pre-cal kids. That doesn't work. To be one of those again, right? Okay. So far, so good, right? Notice what we did there is we combined the product rule with another rule, the sine cosine rule. So as we start learning all of these rules, they are all fair game in any expression or function that we want to differentiate. So it's going to start requiring a combination of rules. All right, my favorite rule, well, one of my favorites, I kind of like them all, is the quotient rule. So here's the incorrect quotient rule. The derivative of a quotient is the quotient of the derivatives. If only, right? What would be the attempt of someone here? It would be, hey, let's take the derivative of the top and let's take the derivative of the bottom and call it a day. And that person would be like, oh yeah, but of course g of x and g prime of x can't be 0, right? Because then we get division by 0. What a foolish person, right? Thoughtful person, don't want to divide by 0, but foolish because they don't know the correct quotient rule. You want to know the correct quotient rule. I know you do. Here it is. The derivative of f divided by g is, it's this here, okay? It's gf prime minus fg prime all over g squared. Gf prime minus fg prime all over g squared. Does that flow as well as f prime g plus fg prime? No. Marcus shaking his head no. And he's right. I mean, that's kind of awkward. G of x times f prime of x minus fg prime gx squared. That is a horrible song, right? That is a weird jingle, right? I would not buy that product. Now, in the product rule, let's come back up here. In the product rule, it's really hard to mess it up, right? It's really, really hard to mess up the product rule as long as you have the spirit of taking turns, right? Because the terms are always added and addition is commutative, right? And the factors are multiplied and multiplication is commutative. So it really doesn't matter the order. Just take the derivative of one and then the other in separate terms, add them together, you're good. I mean, there's a lot of safety built in there. But the quotient rule has subtraction in it. And is subtraction commutative? No. So you got to make sure you do gf prime minus fg prime all over g squared. Of course, where g is not 0. So here's a better way to remember it. Let's call this top function here the high function. High is in like, hello. No, not that high. I spell it like that, but it's high like in he is high, right? Like he was in Panther Canyon, and no, like he is elevated. He is in the numerator. He is high, elevated. And this guy down here then would be the low function, right? But I'm not going to spell it L-O-W. I'm going to spell it L-O, right? That's the cool way, like J-Lo, right? So we really have the derivative with respect to x of the high function over the low function. So high over low, right? That sounds good. But you know what? I am going to, for the poetic sake of alliteration, I'm going to call the low function the ho function. Oh, yes, I am. It is now the ho. Okay? So we have high over ho. Where's the ho? Down low. The ho is down low. The ho is in the bottom. You got a high in the top. He's high. But the ho is down low in the bottom. Okay, so you have high over ho. So if you get high over ho instead of f over g, here's what the rule becomes. It becomes the ho-d-high rule. The derivative of high over ho is ho d-high minus high d-ho all over ho-ho or ho squared. Now what does that mean? This means ho times, guess what d-high means? The derivative of the high function minus the high function times the derivative of the ho function all over ho-ho or ho squared. So it's ho-d-high minus high-d-ho over ho-ho. Ho-d-high minus high-d-ho over ho-ho. That flows, doesn't it, Barker? Ho-d-high minus high-d-ho over ho-ho. Now you're not going to mess it up unless you say it's high-d-ho minus ho-d-high over high-high. The heck is that all about? No. Here's how you remember it. The ho's are on the outside. You start with the ho and you end with the ho. And the ho's are in the bottom. It's all about the ho's here, right? Not the highs. Ho-d-high minus high-d-ho over ho-ho. Start with the ho, end with the ho. You got ho's in the bottom. This is called the ho-d-high rule. It is not the high-d-ho rule. It's the ho-d-high rule. It's all about the ho's. You start with the ho and you end with the ho, and the ho's are in the bottom. All right? Now, I don't know what y'all be thinking, but I'm thinking Seven Dwarfs. I'm thinking Tim Allen and his nosy neighbor, and I'm thinking Santa Claus in a hurry. I don't know what y'all were thinking. The Seven Dwarfs, why the Seven Dwarfs? Hi-ho, it's off to work we go. Okay, why this guy? Did you ever watch his Home Improvement? He'd always come and look over the fence and he'd say, hi-de-ho, neighbor. Yeah, hi-de-ho, neighbor. And then why Santa Claus running? What does Santa Claus normally say? Ho, ho, ho. But you know what? He's in a hurry. So he's like, ho, ho. I don't have time to say the third ho, you know, because I got to go. I'm in a hurry, yo. He has time to say all that, but not the third ho. So Santa Claus in a hurry. So ho-de-high minus hi-de-ho over ho-ho. You got it? Don't forget it. Start with a ho, end with a ho. Ho-de-high minus hi-de-ho over ho-ho. Should we say it together in unison, in chorus, one or two times? On the count of three. Ready? 1, 2, 3. Ho-de-high minus hi-de-ho over ho-ho. Again. Ho-de-high minus hi-de-ho over ho-ho. Get into it louder. Ho-de-hi minus hi-de-ho over ho. One more time, let them hear you on the recording. Ho-de-hi minus hi-de-ho over ho-ho. There we go. Now we've got it. Now we've got it. Let's try it out. I don't even call it the quotient rule. I call it the ho-de-hi rule, okay? When you come in the door from now on, guess how I'm going to greet you? No, not hi-de-ho. I'm going to greet you ho-de-hi. All right, so here we go. We have one function divided by another function. That's a quotient, right? So here we go. The derivative of y with respect to x on the left becomes dy dx. Ready? Ho, you just rewrite ho. D high, what's the derivative of the high function? 4x minus 2 becomes 4. So that's ho d high minus high is 4x minus 2. What's d ho? 2x. Ho d high minus high d ho. All over ho ho or ho squared. Either one. Ho ho or ho squared. Ho d high minus high d ho over ho ho. That's it. The derivative is over. All we have left is perhaps to simplify it. Now here's what I would recommend when we do the quotient rule. Look to see if you have anything that's common right now in the two terms. We do actually, right? There's a 4 here, and I actually have a hidden 4 here. There's a 2 that I have and another 2 I could factor out. That's not going to be as critical as if you had common variable factors. So in this case, I think I'm just going to expand it all out using a sledgehammer. 4x squared minus 4. And here's the most common error on the quotient rule. It is not in generating the derivative. It is in the fact that when we expand it out, we're distributing a negative from one side and a 2x, in this case, from the other side. So if you want to come up here and just write negative 2x, that's what we're distributing. We're distributing a negative 2x. So that becomes a negative 8x squared and a positive 4x. Okay, that can be tricky when you're distributing two things in at the same time from both sides. And all of that is over this. And one last thing, let's just write it in descending order. That's negative 4x squared plus 4x minus 4 all over this. And we'll stop right there for today. We can go a little bit further. We could factor out a negative 4 and see if it actually factors into a quadratic, into a binomial, sorry. But right now that's good. That's the derivative. Ho-de-hi minus hi-de-ho over ho-ho. Notice the domain of the derivative is the same as the domain of the original function. Remember, if it's not continuous, it's not differentiable. So at negative 1 and 1, where we have vertical asymptotes, so does the derivative. Have a fantastic rest of your day. Ho-de-hi, everybody. It means hello and goodbye in here. It's like aloha shalom.